T. Watanabe and Kenichi Yoshida on F-Rationality of Rees algebras under direction of Professor Manoj Kumini. So I'm happy to invite her to present.
Mitra, you may start. Yeah, can I start now?
Yes, please.
Thank you for giving me the opportunity to present my work here. So today we'll discuss F-Rationality of Rees algebras. So the study in this direction was initiated by Anurag Singh. Then the theory systematically developed by Hara, Watanabe and Yoshida, and in a joint project with my advisor, Professor Manoj Kumini, we further study and extend the theory further. So let's begin. So here all rings are commutative, Noetherian, and with unity. Let R be a ring and I be an ideal of R. So a characteristic of R could be anything and I be any ideal of R. Then the Rees algebra of R with respect to I is defined by this R. It's denoted by RIT and is defined as a graded subalgebra of polynomial algebra RT, and it's a non-negatively graded where 0 graded piece is R and the first graded component is I, second graded component is I square, and so on, and T is there just to record the degree of the component. Now the extended Rees algebra of R with respect to Ri is denoted by RIT T inverse and is defined as a graded subalgebra of RT T inverse, and it's a Z graded algebra, and as all non-positive graded T just copies of R, and the first graded component is I, the second graded component is I square, and so on. So it can be seen that the Rees algebra sits inside extended Rees algebra as a summand. Now the third is the associated graded ring of R with respect to I is denoted by GI and is defined as, like, this is also graded algebra whose first graded component is R mod I and second graded component, zeroth graded component is R mod I, first graded component is I mod I square, and n graded component is In mod I plus 1, and so on. So this can be realized as a quotient of Rees algebra, quotiented by the ideal IRT, and also can be realized as a quotient of extended Rees algebra, modulo the non-ideal generated by the non-zero divisor T inverse. So this is the algebraic definition of Rees algebra, but it also has a geometric interpretation. So the base ring R sits inside RIT, the Rees algebra. Hence, the inclusion induces a map from proj RIT to spec R, and this map is the blow-up map of spec R along the closed subscheme V of I, and the exceptional divisor is proj of the associated graded ring GI. So note that the Rees algebra has a unique homogeneous maximal ideal generated by N and T, and we denote the homogeneous maximal ideal as the script capital M. RIT plus denotes the ideal of positive part, such as IT, direct sum, I square, T square, and so on. And GI plus denotes the ideal of positive part of the associated graded ring, such as like direct sum of n greater than 0, GI, and n degree piece. And it is also known that if height of I is positive, then dimension of Rees algebra is dimension of R plus 1, and dimension of extended Rees algebra is dimension of R plus 1, and dimension of associated graded ring is dimension of R, because it's a quotient of extended Rees algebra by a non-zero divisor. So now several properties of Rees algebra has been investigated by many researchers. The property are like Cohen-Macaulayness, Gordon's thinness, normality, and rational similarity. So in this talk, we are interested in F-rationality. So I'll say some known results about these directions. So the first theorem concerns Cohen-Macaulayness of Rees algebra. Let Rn be a Cohen-Macaulay local ring of dimension D. Let I be an imprimary ideal. Then the Rees algebra is Cohen-Macaulay if and only if the associated graded ring is Cohen-Macaulay and the n variant of associated graded ring is negative. Recall that the n variant is the maximum I such that the local cohomology module of associated graded ring supported on Gi plus is non-zero. So the point is Gi is graded ideal, graded ring, hence its local cohomology is also graded, and it is also Artinian. So for a large enough, the graded component has to be zero. So hence the maximum exists, and the maximum I is the invariant of associated graded ring. The next theorem concerns Gordon's thinness of Rees algebra. Let Rm be a Gordon's thin local ring of dimension D. Let I be an imprimary ideal. Then the Rees algebra is Gordon's thin if and only if the associated graded ring is Gordon's thin and the n variant of associated graded ring is -2. Now the third theorem concerns normality of Rees algebra. Let Rn be a normal local domain, I be an ideal. Then the Rees algebra is normal if and only if the In integral closure of In is itself, and this is holds for all positive n. Now I will talk about F-rationality of Rees algebra, but before that I will recall some definition which I talked in previous talk. So just these are the notations that here Rm will always denote a d-dimensional excellent local ring of characteristic P or a graded ring over a field of characteristic P where M denotes the unique homogeneous maximal ideal. We also assume that the residue field R naught M is infinite. The second notation is R naught will always denote the complement of minimal primes of R, and Q denotes Q denotes a power of P, the prime which is the characteristic of the ring, and F R to R denotes the Frobenius endomorphism sending an element of R to its pth power, and F of E denotes eth iterate of F. So now I will recall again the tight closure of an ideal. Let I be an ideal of R. The qth Frobenius power of I is defined by IQ. It's denoted by IQ, and it's defined by the ideal generated by XQ, where X is an element of I. The tight closure of I is defined by the set of all elements X belongs to R, such that there exists a C in R naught, which means C is not in any minimal primes of R, such that C XQ is in the Frobenius power of I for all large enough Q, and it can be checked that it's an ideal. An ideal is called tightly closed if its tight closure is itself. Now we recall tight closure of 0 in the local cohomology module. The tight closure of 0 in HD MR is defined by the set of all elements in the local cohomology module such that there exists a C in R naught, such that C z power Q equals 0 for all Q large. So Last time I defined F-rational rings for any when any arbitrary ring is called F-rational ring. But in this talk, we will be mostly concerned with domain, and those are homomorphic image of a Cohen-Macaulay ring. So we'll define F-rationality only for those rings. So let Ra be a local ring which is equidimensional and homomorphic image of a Cohen-Macaulay ring. Then R is called F-rational if the ideal generated by one system of parameters is tightly closed. A ring R which is not necessarily local is called F-rational if for every prime ideal P the local ring Rp is F-rational. Now I recall some facts also which I discussed last time. The first one is due to Smith. A d-dimensional Cohen-Macaulay local ring is F-rational if and only if tight closure of 0 in the topmost local homology is 0. The second is F-rational rings are Cohen-Macaulay and normal. The third is let R be a F-rational. Let R be a finite type algebra over a field of characteristic 0. Then R has rational singularity if and only if its reduction mod P has F-rational singularity for large enough P. So now I'll discuss some questions which are of interest in F-rationality of Rees algebra. The first question is, let Rn be a Cohen-Macaulay normal local ring. Let I be an imprimary ideal. Suppose the base ring R is F-rational and we assume that the Rees algebra is Cohen-Macaulay and normal. The question is the Rees algebra is F-rational? Now the second question we are interested that let Rm be a same hypothesis, let Rm be a Cohen-Macaulay normal local ring, let I be an imprimary ideal. Then the base ring and the Rees algebra are F-rational is equivalent to the extended Rees algebra is F-rational. So the question is whether these two things are equivalent or not. So why this question one would like to study? Because in case of rational singularity, this question has a positive answer. So it is known that the theorem is also due to Hara, Watanabe, and Yoshida. They proved that if Rn be a Cohen-Macaulay normal local ring, let I be an imprimary ideal, then the base ring R and the Rees algebra rational singularity if and only if the extended Rees algebra is rational singularity. Hence, they are interested whether this theorem has analog in F-rational case or not. The third question is where we are interested is sort of converse of question 1. It says that suppose let Rm be a Cohen-Macaulay normal local ring, I be an imprimary ideal of R. Suppose that the Rees algebra is F-rational. Then can you say that the base ring is F-rational? So now, now I'll discuss all three questions and what regarding these questions. The first question has a negative answer, and this example is given by Anurag Singh. Let R be a three-dimensional Gorenstein ring, which is K, W, X, Y, Z. Quotient W square plus X cube plus Y6 plus Z7 ideal generated by this element, and where K is a field of characteristic P which is greater than 9, and let M be the maximal ideal X, Y. Sorry, the characteristic is 11. I'm sorry, there is a typo. So instead of 9, it has to be 11. So M is X, Y, Z, W. then it is known that R is F-rational. So last time I discussed technique how to show some ring is F-rational. So using that technique, one can show that the ring is F-rational, and the associated graded ring with respect to the maximal ideal is KWXYZ by the principal ideal generated by y square. Hence, the associated graded ring is Gorenstein, and the A invariant is -2. Hence, by previous slide, you can say that that Rees algebra is Gorenstein, and it also can be checked that the Rees algebra is a normal domain. But the point is that Rees algebra is not F-rational. So we have an example which is three-dimensional Gorenstein F-rational ring whose Rees algebra is normal and Gorenstein but not F-rational. So the Rees algebra is not F-rational. This can be seen as follows. So if RMT is F-rational, so are all localization of it. And then we'll see that RMT localized at the point is at the element ZT is not F-rational. So RMT ZT is S ZT 1 by ZT, where S is K U1 U2 U3 Z by the ideal generated by the element U1 square U2 cube Z U3 cube 6 Z4 plus Z5. So S is actually the homogeneous localization of RMT, like bracket ZT, and where U1 is W1 by Z, U2 is X by Z, U3 is Y by Z. And if you can show that S is not F-rational, then RMT ZT cannot be, because it's a faithfully flat extension. So S in the standard grading is not homogeneous, but we define we defined a weighted grading where degree of U1 is 15 and U2 is 8 and U3 is 1, degree of Z is 6. Then, oh, you cannot see the last line. Hello?
Only up to then, you know.
Oh.
Then,
so
up to then we can see. After that we cannot. I mean, at least I cannot.
Okay, then I'll just say the last line is it's not displayed here. So then the A invariant of S is 0, and if it is F-rational, then the A invariant has to be negative. But in this case, with respect to this grading, the A invariant is 0. Hence, S cannot be F-rational, and then the proof is complete. So later, this example was also generalized to higher dimension by Hara, Watanabe, and Yoshida, and they also gave a criterion for Rees algebra to be F-rational in terms of tight integral closure. So I'll define now what is tight integral closure. So definition. This definition is due to Hofstad. Let R be a ring of prime characteristic. Let I be a finite set of ideals, I1 to In. The tight integral closure of I is the set of all elements in R such that there exists a C in R mod, such that C x cube is in the sum of the usual power of ij cube, and this should hold for all large enough cube. Then it can be checked that tight integral closure of script I is also an ideal. And now we'll see two extreme cases of the script I. So the first case is when I is just the singleton set. The set is just one ideal. Then I Then type closure of script type is by definition set of all elements in R such that there exists a C in R naught, such that CXQ is in I Q for all Q large, and which is equal to the integral closure of I. So in this case, the tight integral closure is the integral closure. The next case is when I is a set of principal ideals. Principal ideals are x1, x2, and xn generated by this. Then the tight integral closure is again using the definition set of all elements in R such that there exists a C in R naught such that CXQ is in the sum of the right hand side here, and this should hold for all Q. And now see, this is the condition. This set is exactly the tight closure of x1 to xn. So in this case, the tight integral closure is the tight closure of the ideal generated by x1 up to xn. So in this sense, tight integral closure is a generalization of tight closure and integral closure. So now I will just recall the definition of reduction. Let I be an ideal of R. In subideal J is called a reduction of I if In is equals J In minus 1 for some positive n. A reduction is called minimal if there exists a subideal K such that K is also a reduction, then the K has to be J. Then we will recall some facts. If J is a reduction of I, then they both have same radical. Second is let Rn be a d-dimensional local ring with the residue field is infinite. Then for any imprimary ideal I, there exist elements x1 to xt in R such that x1, the ideal generated by x1 to xt is a minimal reduction of I. And note that the x1 up to xt is a SOP because these two have the same radical. So now I'll say the theorem which gives a criteria for F-Rationality of Rees algebras, and it is due to Hara, and Yoshida. So let Rm be a d-dimensional excellent Cohen-Macaulay normal domain of prime characteristic. Let I be an imprimary ideal, and J is F1 up to Fd is a minimal reduction of I, which exists. We saw in previous slides. Then the Rees algebra is F-rational if and only if the following two conditions hold. First one is the Rees algebra is Cohen-Macaulay, and the second one says for all k greater than equals 1 and for all n less than kd, the tight integral closure of this set of ideals is In plus the ideal generated by f1 power k, f2 power k, fd power k. So now I will say what is the second condition in elaborately. Condition 2 says if there exists element C R naught in and X in R such that CXQ is in the ideal here. So this is the condition for X to be in the tight integral closure of this. And then the condition is saying that if this satisfies for all large Q, then X should belong to In plus F1k to F3k. So now, so Rees algebra is F-rational. Then the first condition is like one can hope that okay, so if it is F-rational, then it has to be Cohen-Macaulay, and to prove something F-rational, one could assume that it's Cohen-Macaulay. But how this condition comes? To get a feel, I would like to sketch a proof of this theorem. So I'll say only the steps. So recall that script capital M denotes the homogeneous maximal ideal of Rees algebra. The first step is, in order to show that the Rees algebra is F-rational, it is enough to show that it is F-rational only at the homogeneous maximal ideal. And the step 2 is, hence, since our the Rees algebra is Cohn-Macaulay, then it is enough to show only that the tight closure of 0 is 0. Notice that the top local homology supported on maximal ideal M is same as the top local homology of R3 localized at capital M. So hence the tight closure of this is same as the tight closure of the top local homology module of RIT localized at M and supported on M. Now the step 3 is the crucial. So the crucial, it's important that there exists this commutative diagram of like this commutative diagram, and so here one can see that the right hand side, that HD plus 1 M RIT, it's a homogeneous, it's a graded module, and it's only the module supported only in negative degrees. See, that is why this N is less than 0. So using the diagram chasing of this, we would like to say that tight closure of 0 is 0. So take any element in the tight closure of 0 from this module on HD plus 1 M RIT, and then take a lift here on the left hand side, that HDMR, and then since it is a tight closure of 0, that element goes to 0 on the right vertical arrow, and the lift also goes via this commutativity of diagram. So next slide, I'm just saying this, that let eta be a tight closure of 0, and then let psi be a lift of eta. Then since this is eta is tight closure of 0, then eta goes to 0, and hence C Fe psi also goes to 0. So this goes to 0 means that CFE is image of phi. So where phi is the left map. So now in the lower exact sequence, we get CFE psi, which is an image of phi. So now we want to say that closure of 0 is 0. We want to show that if CFE psi is an image of phi, then psi is in the image of phi. So we want to show this the claim. So now let's see what is the map, the phi. The phi is sorry. So the phi is the left map, left horizontal map. So note that F1T, F2T, and FDT generates RIT plus up to radical. Hence, the HD RIT plus RITN, this is the set of all elements. It's a fraction R by F1, F2, FD T power n, where L is bigger than 0, and it's a n degree. So the degree of R has to be DL plus n. And in the Rees algebra, DL plus n degree piece is I, DL power n plus 1. And similarly, that F1 up to FD is a SOP. So HD MR is also can be, the set is just a fraction of R F1 to FD, L greater than 0. But here R could be anything in the ring. And now the map phi is just take the element and send as it is, because see, this element in HD RIT plus RITN is, it can be also can be realized as an element in HDMR. So now I say what is this left horizontal map phi. Now the proof will be complete if we use the following fact, that an element B, this fraction B by F1 FDL in the type in the local homology module of R it will be in the image if B is in the ideal IDL plus N plus F1L F ideal generated by F1L to FDL. So using this fact, we will prove the claim. So suppose Xi has this form. So Xi is an element of HDMR, and the hence C of Fe Xi is also is just the raising the qubit power. Then C of Fe Xi is in image phi. Then using this condition, it says that CRQ is in ideal DLQ plus NQ plus F1 to LQ to FD to LQ. And Xi will be, because we want to show that C Fe Xi is in image of phi if, like, if and only if Xi is in image of phi. So these two we want to see the equivalence. So again, the Xi is in image of phi. Again, this fact that R will be in IDL plus N plus the ideal generated by F1 to FDL. So in order to see the equivalence of the left hand, so it is enough to see the equivalence of the right side of these two equations. But the equivalence of right hand side of the above two equation is precisely the condition 2, the typed integral closure. Hence, this condition is in the criteria. So next, I'll say that the question 2, which says that the extended Rees algebra, if rational, whether it is equivalent to the Rees algebra and the base is if rational or not. So in a joint work with Manoj Kumini, we prove this positively, that let Rm be a d-dimensional Mitra Koley local ring, let I be an imprimary ideal, let R and the Rees algebra is F-rational, if and only if the extended Rees algebra is F-rational. So remark that the only if direction means that suppose we assume that the base ring R and the Rees algebra is F-rational, then the extended Rees algebra is F-rational. Was proved by Hara, Watanabe and Yoshida, and they conjecture about the if part. And yeah, they conjecture because again this theorem has analog in rational singularity, and they mention there also. And they also mention that if part is important because suppose one could show that GI is F-rational, then T inverse being non-zero divisor implies that the extended Rees algebra is F-rational. Then by our theorem, the Rees algebra will be F-rational. So suppose we have a ring which is a graded hypersurface ring, and if suppose this is F-rational, then the associated graded ring with respect to the maximum homogeneous ideal will be isomorphic to the ring itself, hence it is F-rational. Then by this, the second remark, one can say that the Rees algebra is always F-rational. And also one other advantage of the if direction is the existence of homogeneous system of parameters of extended Rees algebra. So in order to see that extended Rees algebra is F-rational, so one just needs to show that the homogeneous system of parameter is tightly closed. Now I'll sketch the if direction, and our machinery also gave alternate proof of the only if direction. So if direction means we assume that the extended Rees algebra is F-rational, then we showed that the Rees algebra and the base ring is F-rational. So in our so the first is the base ring is F-rational. So that is easy because the extended Rees algebra localized where at T inverse, at the element T inverse is T inverse, which is also F-rational because localization of F-rational rings are F-rational. And now our T inverse is faithfully flat over R. Hence R is also F-rational. And the second one, to show that RIT is F-rational, so the proof has two parts. First, we show that the Rees algebra is Cohen-Macaulay, and the second, we showed that the tight closure of 0 is 0. So now I'll go back to the theorem again, and then would like to say that note that the extended Rees algebra sits inside extended Rees algebra as a summand. So if one could prove that if that the direct summand of F-rational ring is F-rational, then this would give a one-line proof of the if direction. But unfortunately, for F-rationality, this is not true. That direct summand of F-rational need not be F-rational. But for the rational singularity, it is true, and that is how the rational singularity case the proof goes. Like the if, for the rational singularity case, the if part was the easy part, and the only if part requires some work. Now, notice that Singh's example was three-dimensional ring. Three-dimensional Bodenstein F-rational ring, whose Rees algebra is Bodenstein and normal, but it's not F-rational. But one might ask that what about the two-dimensional case? So two-dimensional result has a positive answer. It says that let Rm be a two-dimensional F-rational ring. Let I be an integrally closed imprimary ideal. Then the Rees algebra is always F-rational. So I'd like to mention that this theorem also has an analog in rational singularity, which says that let Rm be a two-dimensional rational singularity, then let I be an integrally closed imprimary ideal, then the Rees algebra is always rational singularity. And this theorem is due to Lippmann. And this theorem is also proved by Hara, Watanabe, and Yoshida. And the key steps are they first prove that the Rees algebra is always Cohen-Macaulay and normal, and then they showed that if xy is a minimal reduction of I, then they showed this tight integral closure condition. But as a consequence of our main theorem, we also get a proof of this theorem, which I'd like to discuss here. That so we show that the extended Rees algebra is F-rational. Hence, by our theorem, the Rees algebra will be F-rational. So note that xy is a minimal reduction of I. Hence, xt, yt, and T inverse is a homogeneous SOP for the homogeneous maximal ideal of the extended Rees algebra, and things it's enough to show that this tight closure of the homogeneous SOP is tightly closed. So here we recall that J is the ideal generated by X and Y. So let alpha be an homogeneous element in the tight closure. So note that since xt, yt, T inverse is homogeneous ideal, its tight closure is also homogeneous. And it's to show that tight closure is itself with enough to check only on the homogeneous piece. So let alpha is of the form A ck, which is in the tight closure of xt, yt, T inverse, where A is in ik. Then I'll do the case only when k equals 0 and k equals 1. The other case are easy, and so I left this. So if k equals 0, then since this alpha is in tight closure, there exists a C in R0 such that for all q large, C alpha q, which is equals to C a power q, has this expression in terms of xt, xq, tq, yq, tq, and t inverse minus q. So has this expression where A1, A2 is in the ring R, but A3 is in the Q graded component. That is why A3 is in IQ. Hence, CAQ is in I power Q for all large Q, which says that A is in the integral closure of I, but I is assumed to be integrally closed. Hence, this is in the ideal I. Hence, A is in the ideal xt yt T inverse. Now the next case is when k equals 1, then there exists a c, again as same as the case 1, there exists a c in R naught such that for all q large enough, c alpha q is of this from c aq and tq, and has this expression. But here again A1, A2 are in R, but A3 has degree T. A3 comes with T power 2Q. So the degree of A3 is 2Q, hence A3 is in the I power 2Q. So now using a result of Lippmann and Tessier is saying that I square is always Ji, then I power 2Q is J 2Q minus 1I. And now note that J is generated by two elements, X and Y. Hence, J power 2Q minus 1 is inside J Frobenius power of Q. Hence, in the expression here, each part, this part, and this part is inside J Frobenius power Q. Hence, CQ is in J Frobenius power Q for all large Q. Gives A is in the tight closure of J, but now J is a system of parameter for the base ring, and the base ring is assumed to be F-rational. Hence, A is in J, and hence AT is in JT. That alpha is in the ideal generated by xt, yt, and T inverse, and thus the extended Rees algebra is F-rational, and uh, and hence the Rees algebra is also F-rational. So now I'll give the partial answer to the question 3. The question 3 was that suppose R is a ring of Kuhn-Macaulay and the Rees algebra is F-rational, then whether the base ring is F-rational or not. So let's see whether what about this question for rational singularity. So in this case also see that the base ring is a summand of the Rees algebra. Hence the Rees algebra as has rational singularity will say that the base ring also has rational singularity. Hence question 3 always has positive answer for rational singularity case, but for F-rationality, question 3 in general answer is no. We see one example, but first see the case when the Rees algebra is Gorenstein. So when the Rees algebra is Gorenstein, then in this case the base ring always be F-rational. So we assume that the Rees algebra is Gorenstein and F-rational, then it will say that the base ring is always F-rational. So this can be seen easily because since RIT is Gorenstein, it is F-regular, and normality of Rees algebra will imply that R is also normal, and hence it is a domain, and hence the Rees algebra is also a domain. Let S be the Rees algebra localized at the homogeneous maximal ideal M. Let J be an ideal in R. Now J type closure of J in S is a subset of JS whole star, and which is equals JS because S is weakly F regular. Hence J star equals J star S intersection R, This equality follows because R is the direct summand of S, and J star S intersection R is a subset of JS intersection R, and which is equals J again because R is the direct summand of S. So here we showed that R is actually every ideal is tightly closed. So R is actually weakly F regular. So now we return to the general case. Suppose RIT is just F rational. Hence, it is Cohn-Macaulay, and then we know that the invariant of associated graded ring is less or equal to -1. Then, uh, uh, then this is a theorem due to Hara, Watanabe, and Yoshida. They proved that Rm be a d-dimensional Cohn-Macaulay local ring, and I be an imprimary ideal of R. Assume that the Rees algebra is F-rational if the invariant of G of I is strictly less than -1, then the base ring is always F-rational. But then what about the case when A invariant is -1? So when A invariant is -1, then the A invariant is -1 and the Rees algebra is F-rational, then the base ring could be either F-rational or could be not F-rational. So we'll see two examples. So first example is let R equals K XYZ modulo the principal ideal generated by x square plus y square plus z square, where K is a field of characteristic P. Let M be the ideal generated by x, y, z. Then R is a two-dimensional F-rational ring. This can be again using the technique I discussed last talk. One can show that it's a two-dimensional F-rational ring. Then integral closure of maximal ideal is the ideal itself. Hence, by the two-dimensional case, that the Rees algebra will always be F-rational. Now, what is the associated graded ring? The associated graded ring with respect to the maximal ideal M is isomorphic to the ring R itself, and thus the invariant of G of M is -1. So here we have an example where the Rees algebra is F-rational and the invariant of associated graded ring is -1, but the base ring is also F-rational. So next we'll see that the base ring need not be F-rational. So this is the example. Let R be K XYZ quotient by the ideal generated by z square plus x square y plus xy square, where K is a field of characteristic 2. Let x, y, z equals the ideal denoted by M. Then the Rees algebra RMT is F-rational. The proof was given by Hara, Watanabe, and Yoshida. They proved that the Rees algebra is Cohn-Macaulay, and then they proved that if x and xy is a reduction of M, and they showed that the tight integral closure of this set, that M2L minus 1 XL YL is the ideal M2L minus 1 plus XL YL, ideal generated by XL YL. But R is not F-rational because see, X and Y is an SOP and Z is not in the ideal generated by X and Y, but Z is inside XY, tight closure of X and Y. Because from here, Z square is in the ideal generated by X square and Y square. Hence, it is in the tight closure of XY. So R is not F-rational, but the Rees algebra is F-rational. Note that the associated graded ring with respect to the maximal ideal is kxyz mod z square, and invariant of the associated graded ring is -1. So here we have an example where the associated graded ring, invariant of associated graded ring is -1, and the Rees algebra is F-rational, but the base ring is not F-rational. So we prove that extending their result, that let Rm be a d-dimensional Cohen-Macaulay local ring and I be an imprimary ideal of R. If R is F-rational and HD Gi plus Gi, this local cohomology module of Gi supported on Gi plus, and then the -1 graded piece. To this F denotes the Frobenius action. To HD Gi, the local cohomology of Gi supported on Gi plus on the -p part. If Frobenius takes -1 piece to the -p piece injectively, then we can say that R is F-rational. And as a corollary, we recover Hara, Watanabe, and Joshida's result. Like, because since A invariant is strictly less than 1, then this term, that -1 degree component, is 0. Hence, this condition vacuously satisfied. So, R is always be F-rational. The next, I'll say that this gives a sufficient condition. This theorem gives a sufficient condition for base ring to be F-rational, but it is not a necessary condition. I'll see this example. Let R equals kxyz modulo the ideal generated by x square y cube z to the power 5, where k is a field of characteristic p greater equals 7 and m equals x, y, z. So last time we saw that R is an F-rational ring and m bar, the type integral, the integral closure of m is m itself. Hence, by the two-dimensional case, RMT is F-rational. Now, note that that the associated graded ring is isomorphic to kxyz by x square, and we'll see that the Frobenius action on the top local homology of GM is not injective. So take so YZ is SOP for GM, and then this can be computed from the check complex of CYZG. And note that X is not in the ideal generated by Y and Z, and G of M is Cohen-Macaulay. Hence, this X, the fraction, the cohomology class of the fraction, that X mod YZ is a non-zero element of H2 G, the H2 GM plus, and that it's a homogeneous of degree -1. And the Frobenius F of X modulo YZ is just the quotient XP mod YP ZP, and then take the homology class. Now X square is 0 in GM, hence this is 0. Hence the action of Frobenius on local cohomology of GM on -1 piece to -p piece is not injective, but the Rees algebra is F-rational and the base is also F-rational. So this shows that it's not a necessary condition. Yeah, I am done. Thank you. And if anybody has any question, please.
Well, I have a question. I'll start.
Yes.
See, in the case of Cohen-Macaulay-ness as well as Gorenstein-ness, there was a strong connection between these properties of Rees algebra and associated graded ring.
Yes.
What about in this case? Like, I don't see, it may be hidden in proofs. I don't know whether you're really talking about the
Also, yes.
rationality of GI.
But I said here that if one can show that if GI is F-rational, then the Rees algebra will be F-rational by this theorem, by our theorem. So I'll just say where I say this. So this thing, that the remark, the second remark.
Okay.
Let R is F-rational, then T inverse being non-zero divisor, then extended will be F-rational. But the converse is not true. Like suppose the base, the ring, like
The converse is not. You're saying it is not true, or it is? I mean, you have an example where it is.
I mean, if the Rees algebra is F-rational, then associated graded ring need not be F-rational, because this is the there could be example like because there are examples where the base is isomorphic to the associated graded ring, right? And then we said that the Rees algebra F-rational does not imply the base is F-rational. So
Okay. Yeah, I got it. Thank you.
There's a question from Sridevi.
Yes.
What about the non-M primary ideal case?
That non-M primary ideal case, I do not know. Even for I do not know condition for Cohen-Macaulay-ness. Like I think they are trying to say this thing for the maximal ideal and then the M primary ideal, but not M primary ideal. I do not know.
No, for non-M primary ideal, there are.
And also there are, like when R is regular and I is, there are examples of non-M primary ideal. I think this is an example of Khoury, who shows that R is regular and I is not M primary. Then the Rees algebra is not F-rational.
Okay.
But any condition that I do not know.
No, there are theorems about Cohen-Macaulay property of Rees algebra for non-M primary ideals.
Yes, but I think for F-rationality, the condition, I don't think there are conditions.
What about, do we know anything about F-rationality of the fiber ring?
Fiber ring? No. No, there is no,
There are no results.
No, I don't think.
Professor Watanabe is in the audience. I can ask him if there are any questions, any results about the fiber cone being F-rational.
So I don't know. Perhaps. So how about Yoshida? But anyway, I enjoyed the talk very much. Thank you very much.
I don't know.
So there are no works on the F-rationality of fiber cone. At least I have not seen.
Well, I can't. Yeah, I don't know. Sorry.
Okay. Right. And what about the multigraded case?
For the multigraded case, I think in the paper of Hara, Watanabe, and Yoshida, they proved also that the two-dimensional case, they proved the analog. Like I1, I2, IN, and then there are the results in that paper. But for higher dimensional, there is no result. At least I do not know. only positive results for tangent to Rees.
Yeah. Are there any other questions from audience?